So my name is Martin Wegener. I'm from Karlsruhe with all these affiliations that you can see there. And I'm supposed to tell you something about cloaking. We are experimentalists, so we do some design, we do some numerics, but the emphasis is really on making of things and looking whether they work. So this is about using coordinate transformations for design. And one of the reactions I sometimes get is that, oh, coordinate transformations, that's something very abstract and very dry. So let me lead you away from that, because coordinate transformations are a big part of Photoshop. Not everything in Photoshop is coordinate transformations, but if you think you are too fat or you dislike some part of your body, what Photoshop can do for you is it puts a grid of coordinate lines onto a photograph, and then you locally stretch or locally compress part of the image and change it as you wish. So what you do technically is you perform a coordinate transformation. You go from some old coordinates, x and y, that's what you see as a grid, to some new coordinate, call them x prime, y prime, whatever you want, and then you represent them in the old coordinate system. And what it can mean is that, for example, you stretch my nose here in this part and you compress other parts, and at the end you forget what you've done and you got a desired result. Maybe this is not exactly desired, but you can do more beautiful things. So to me, coordinate transformations are very intuitive. Loosely speaking, it's like a distortion of some grid. Think of a rubber sheet that you have in front of you and you pull on it. And the aim is now to translate this fictitious coordinate transformation into something real and do something meaningful with it. That's the whole point. So this is the outline of this presentation. I'm not going to make all these points, and to be honest with you, this was prepared for a much longer school last year. But we can look at this table of content from different perspectives. First of all, we can say that I may speak about optics, thermodynamics, and mechanics. So maybe I focus a bit tonight on optics. That's what I spare out tomorrow morning. So that's one way of looking at it. If you like optics, there are two parts of optics. One is what you might expect from optics, Maxwell equation type of optics of continua. But there is also another part that you may have not expected, and that is optics in the regime of the diffusion equation for light. And there are actually more things you can do there. And you can also look at it from another viewpoint. You can use coordinate transformations in many different ways. I guess the oldest one is to use it for transforming boundaries. The most famous one, I guess, is using it for transformation of material parameters, to design material parameter distributions. Something I would like to show you is that you can also use it for transforming surfaces to do special things in optics. And maybe if I have time at the end, I'll also show you something about direct transformation of lattices, of discrete lattices. So that's the plan. So let me start with something very old, and that I guess you have heard, and that is using coordinate transformations in mathematics to solve problems. And this is a famous fluid dynamic problem. If you have fluid dynamics, you usually start from a continuity equation for the current density, the mass current density. The divergence of the mass current density times the derivative of the mass density is 0. That's how you can describe fluid flow in many situations. And then often you can assume that the liquid is incompressible. Then you have that the divergence of the current density is 0. And if you then remember that the current density can be written as the mass density times the velocity, and you write the velocity in the regime of laminar flow as the gradient of some potential, then you get the divergence of a gradient, you get a Laplace equation. And you've all seen this before in many different areas of physics. And I guess in fluid dynamics, coordinate transformations were used first, because you can get analytic solutions, for example, for a fluid flow around a cylinder. The issue there is that you have to solve it under certain boundary conditions, and here that the normal component of the current density is 0, because the fluid cannot flow into the solid. It's pretty obvious. It can flow tangentially, but not into the boundary, and that's why this component has to be 0. So if I now ask you, please solve the differential equation for this wing type of structure, you will have a very, very hard time finding an analytical solution. But if you start from the solution for fluid flow around a cylinder, and then you come up with some coordinate transformation that transforms a cylinder into this strange boundary here, then you can apply this coordinate transformation to this equation here, and it turns out that a special class of transformation, so-called conformal transformations, preserve the local angles. I will tell you more about that later on. And if the local angles are preserved, what has been normal to the surface will always stay normal to the surface. And then by simply transforming the solution that you have, you can get solutions for very weird situations. And there are thick books on that, what kind of solutions you can get. And this is not a typo here. This is more than 100 years old, this textbook. And this has experienced quite some renaissance lately. People like John Pendry or so have been using the same trick in electromagnetism, in plasmonics, for example, where you have a similar equation, a similar Laplace equation, and where you have a similar problem. If you have a metal, you have a boundary condition on the metal, that the electric field is zero, the tangential component of the electric field is preserved, and you can use all the old tricks from more than 100 years ago and copy them in electromagnetism and get solutions for whole classes of different problems. There's a bulk of literature about that now. Just to remind you that coordinate transformations are not really new to physics at all. But what is maybe more popular now is using them for getting material parameter distributions, and I would like to explain that. So let me jump to this table. I told you a little bit about this equation here. In fluid mechanics, I pulled out the mass density when I showed it to you, but the mass density was constant, so I may as well pull it in to this equation again. And the reason I'm showing you this table is that I hope you see that many problems in physics are mathematically just the same. So if you compare fluid mechanics with electrostatics, that I guess many of you have seen in optics or nano-optics, the electrostatics is a good approximation. It's technically the same thing. You just have to replace the mass density by epsilon. You have to replace the scalar fluid potential by the electrostatic potential. It's just the same thing. You can copy everything one-to-one in these different areas. You can copy it to magnetostatics, you can copy it to particle diffusion, heat conduction, electric conduction, even to the Schrödinger equation. Just that everything fits on one view graph. I have considered the static case here. Everything is static. Did I write this somewhere? Yes, it's always the stationary case. But this is fine, because I will consider spatial coordinate transformations and not temporal coordinate transformations. So not much changes if you add the temporal part to these equations. But again, I've written it like that, otherwise it really doesn't fit onto one view graph. So one thing you could do to the same equation that I just showed you is the following. You can say, well, I perform a coordinate transformation, and then there is something that should be in every textbook. It's a kind of substitutional law, and that is you start from this generalized Laplace equation that I just showed you. Divergence of, in this case, the mass density times the gradient of the potential is zero, and you apply this coordinate transformation. I mean, this is the gradient with respect to this coordinate, and you substitute everything. If you actually do this, it's going to be a huge mess. Trust me. And if you are in a good shape and go through a couple of pages of math, you can rewrite this equation and you can bring it back into the exact same form, except that you have to replace the scalar mass density that I've started from with this expression here. You have to replace it by a tensor that describes an anisotropic behavior. And this tensor is related to the Jacobi matrix, which is simply the matrix made up by the derivatives of the old coordinates with respect to the new coordinates with respect to the old coordinates. You don't have to understand this in detail here, just trust me, there is this expression. People have derived it for you. Actually, many people have derived it independently in the literature without citing each other, and I will give you a few examples for that. But if you take this equation, it's in principle straightforward to compute from a known coordinate transformation, from some stretching like I showed you in the beginning, Jacobi matrix, and then the new material parameter distribution that gives you exactly the same behavior as if this coordinate transformation was real. This is a bit abstract, but I hope I can make this more concrete in a moment. So here you might ask, I mean, what the hell does a anisotropic mass density mean? And I think it has no meaning. It's just a mathematical thing. But now you can do what I told you. You can jump to the left here and do the very same thing for electrostatics in your head and replace this rho by epsilon. This would be your electrostatic potential, and then you get some anisotropic distribution of epsilon of the electric permittivity. And this you can realize experimentally, and this has a meaning. Okay, so this is like a little recipe here. So the first thing you want to do if you want to use these kind of tricks is you have to check whether the equations you talk about are form invariant. And I say again, this means you do a coordinate transformation, blah, 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 and you bring it back to the exact same form as the one you started from, except that you have new effective material parameters. And many equations that you know are form invariant under coordinate transformations. The Maxwell equations are, Schrödinger's equation is form invariant, and the many equations I've shown to you are. And then you have to be creative. You have to come up with something to get some behavior that you want. You do some math, that's straightforward, but then there is a big issue for experimentalists. If you get some anisotropic, inhomogeneous distribution of the electric permittivity tensor, how do you realize this experimentally? And there is no straightforward recipe that tells you do it like that and you will be successful. They need some brain, you need some inspiration, and you need some experience to actually make it work. So let me give you a more intuitive explanation, and this uses a special class of coordinate transformations that aim at getting cloaks, making things invisible. And I try to illustrate the coordinate lines that I showed you before by these streets. And on these streets we have cars driving. If you like, think of the cars as representatives of photons in free space. And the cars can drive here and everything is nice. And now we perform a coordinate transformation that John Pendry has come up with in the year 2006. It's more than 10 years old by now. And what this coordinate transformation does is it takes a point, and conveniently this point will be located in the middle of this little lake here. This is my old coordinate r, and I do this linear transformation that transforms this point into a finite circle. So r equals 0 is going to be transformed to r1, and that's the circle into which we transform a point. And if you visualize this transformation, it looks like this. I can go back and forth a couple of times. This is the original network, and this is now a fictitious, distorted network of streets. And the cars, if you look at them like on a computer monitor, will drive around this void here. And that's the whole point. In this void you can later put things and hide them, make them invisible from the surrounding. But now the question is, how can we map this fictitious coordinate transformation onto material parameters? And here you have to just remember some very basic things of optics. What matters in optics is the optical path length, basically. So if in this configuration every optical path length between two street crossings, say from here to here, is the same as the optical path length from here to here. This is the same street, just distorted. This is the little lake. I'm looking at this street, which now gets transformed into this part here. If the optical path length of this thing is the same as the optical path length of this here, then these two situations are going to be equivalent, optically speaking. They're just going to behave the same. And if I stretch this street by a factor of, I'm guessing, 5 or 6 here, and the optical path length is supposed to be the same, then this means you have to reduce the refractive index by a factor of 5 or 6. Because loosely speaking, the optical path length is the product of the refractive index times the geometrical path length. Stretch by a factor of 5, divide the refractive index by a factor of 5, and you're done. That's a much simpler version of the same thing I showed you before mathematically. But you see it's anisotropic. In this direction I have stretched the street. In this direction I have compressed the street. So here in this direction light has to get faster. Here it has to get slower. It's anisotropic. That's the same tensor I showed you before, just a bit more intuitively. So it's very simple, and if you follow this guideline, you can construct a cloak. Just look at this image. You have to have a lower refractive index for light propagating in this direction, in this region, and for this direction it has to be a higher refractive index than what you had before. Very simple. But if you now switch on your brain, you will find out that there are fundamental limitations, things that are not connected with difficulties in fabrication, but connecting with fundamental laws of physics. And here I try to make it as simple as I can. What you want is that light goes from point A to B in the same time as in free space. In free space it would go the straight connection here. But now you somehow magically want light to go around the object. That's what I showed you. And you want this to happen in the same time as the straight connection. But this is obviously geometrically a detour. So light has to be faster than the vacuum speed of light in this region if vacuum is your surrounding. So you need superluminal velocities. It's the same in the picture I showed you before. Now this should not bring you into a crisis. Phase velocities larger than the vacuum speed of light are nothing unusual. In every metal above the plasma frequency you have phase velocities larger than the vacuum speed of light. But if you want this now to be broadband and macroscopic in free space, that is in vacuum, then there is an issue. Because if you want this to happen for all colors of visible light, say, you want dispersion to be negligible. And if dispersion is negligible, then the phase velocity is equal to the group velocity is equal to the energy velocity of light. And then the situation that you aim at would mean that the energy velocity of light is larger than the vacuum speed of light. And this is forbidden by relativity, because superluminal energy transport also means superluminal mass transport, and that is forbidden as much as we know from the theory of relativity. So you can't do this in vacuum. You cannot build a macroscopic broadband invisibility cloak in free space. And you might ask yourself, so why then is this guy standing in front of me and telling me these things? Well, this is a limitation. You can't do it, period. But if you understand this limitation, you can sneak around it in many situations. For example, if you go away from vacuum and do a Gedanken experiment in water, there the refractive index is 1.33, light is slower. So there you have some room, not much, 33% to go up without hitting this fundamental barrier. And I'm going to show you an example like that, not in water but in a dielectric surrounding. And if you had, which we do not, but if you had a refractive index of 100 or 1000, a material that has that, then you would lower the speed of light so much that you have very much room to go up and you could do fantastic things. Unfortunately, nobody has such a material with broadband performance. Also, if you forget about light and talk about sound waves or elastic waves or heat conduction or electric conduction, then the velocities involved are so slow compared to the vacuum speed of light that you can forget about this relativistic argument altogether. And then you can do this very nicely. You can do broadband, macroscopic acoustic cloaking in principle. Nothing prevents you from doing that. There's no law that holds you back from doing that. Okay. And that's basically what I'm telling you a little bit in these different chapters here. Now I'm telling you how you can sneak around this fundamental limitation and get broadband cloaking still. And then maybe later I'll show you some examples from thermodynamics. So I mentioned conformal maps. This is totally well known, just in case you have forgotten for a moment. A conformal map is just a complex function, and we interpret the real part and the imaginary part of the imaginary number, the complex numbers here, as the spatial coordinates. So I write a complex number, and x would be my horizontal coordinate, y would be my vertical coordinate. And if you take any function of this original coordinate, you get some new function. So it transforms in two-dimensional space from one set of coordinates to a new set of coordinates. And the beautiful thing is that this very complicated thing that I showed you with the Jacobi matrix, this simplifies tremendously. And this is pretty much the same thing that I showed you with my simple picture. And I think Ulf Leonhard showed this for the first time. For these kind of transformations, you get a locally isotropic refractive index. No tensor properties, no anisotropies, because you preserve local angles. What used to be isotropic stays locally isotropic, and then you get a very simple law, basically, that the refractive index is replaced by the original refractive index divided by the stretch factor. That's what I told you before. If I stretch by a factor of 5, I have to divide the refractive index by 5. This is basically what this law tells you. So here it's a hell of a lot simpler to get refractive index distributions than in the more general case. And it's also more feasible because here you don't need crazy anisotropic materials. You just need a graded refractive index. It's as simple as that. And one of the early examples that John Pendry and Jensen Lee have come up with in 2008 is this Carpet Cloak. This is some very old thing, but I tell it to you anyway because I would like to get to something more new. And the idea here is not to hide something in free space, but hide something under the carpet, hence the name, kind of. So what I mean by that is that the transformation that they introduced is not starting from a point and making a point finite in size, but rather starting from the edge of space. So in optics, this will be a mirror, for example. Light cannot go beyond this mirror. People in microwave physics call it a ground plane. And you transform this edge, and then you don't get crazy parameters. If you do this gently, you see that the stretching or compression factor is not so large here, and you get away with fairly moderate refractive indices. And then you can make these things actually. So this is the structure that we designed a while ago here. So the story is you want to hide something, you put it on the floor, you put this metallic carpet on top. You can't see through the carpet, but then every idiot will see that there is some bump on the floor and you will get some distortion of this curved metal surface. And then this coordinate transformation gives you a refractive index profile that you're supposed to put on top that will make this curved carpet look flat and hence unsuspicious. You will not see anything. It will look like a flat mirror. So it's not a big surprise. Here you have a higher refractive index on top of the bump. This kind of compensates the lack of optical path length that you have here. You add some optical path length by increasing the refractive index. And here you have the opposite problem. Here you reduce the refractive index. So this picture contains no scale. To some extent, this is not a problem because this is scalable. You can put any scale you like to this picture. Only the aspect ratios here matter. But what I should tell you is what these colors mean. And I tell you the maximum, the red refractive index here is 1.5. And the minimum refractive index is 1. So this means we do not go above the vacuum speed of light here. And hence this can be a broadband structure. And the environment is something like an index of 1.2 in this case or so. So wait a second. So how do we make this? There's a trick we are going to be using again. We make this photonic crystal, but we don't use it in the sense of a photonic crystal. We rather use it in the long wavelength limit, such that the light field averages over these periodic structures here and just sees an average refractive index. And as a result, we simply have to tune the volume filling fraction of this structure. It's basically simple. If you have 0% of the polymer in this case, you get the refractive index of air. If you have 100% of the polymer, which is almost the case here, you get the refractive index of the polymer, and in between you get something in between. We've done this more fancy with photonic band structure calculations, but basically that's the story. So just make a three-dimensional dielectric structure and play with the volume filling fraction. And that's how we do this. We use 3D laser printing or 3D direct laser writing. So we take very tightly focused femtosecond laser pulses, and then by means of 2-photon absorption, that's important, or some other superlinear process, we concentrate the energy in a tiny volume. In this volume, a chemical reaction takes place. We convert a liquid monomer, usually into a solid polymer, and then we wash out the liquid monomer and get basically a three-dimensional digitized version of what we have programmed. And this is a technology you can buy today, and you can make very fancy structures with that. I'm going to show you operation at visible frequencies, and you should ask yourself, how can it be that this guy shows me structures written with 800 nanometers wavelength of light? That was the wavelength that we are using here. Yet they are so small that they look like an average structure for visible light. How can it be that I write structures that are so much smaller than the wavelength of light? At least I learned in school that this is impossible. And here we are stealing tricks from optical microscopy that I guess you have seen. Stefan Hell got the Nobel Prize in chemistry 3 years ago by now for that, for introducing this STED trick, stimulated emission depletion. And we have converted that to lithography, to laser writing, and we do it a bit differently than people do it in microscopy. So we have this normal laser focus, which has a maximum right here in the middle. It's actually red light. We use 800 nanometers wavelength, 2 photon absorption, so effectively that's at 400 nanometers wavelength. And then we have this weird bottle beam focus here. Send the laser through a phase mask and get this awkward focus that has a 0 right there where the other focus has its maximum. And the idea is that you need a special resist that you can excite with red light, but that you can de-excite with green light. And the trick is basically, and that's why Stefan Hell got the Nobel Prize, that this green focus is touching 0 intensity at one point, and one point has no extent. And that's why you can get infinitely small resolution on paper. In reality, there are always some limitations. So in other words, we excite with this red thing and then we eat away with this green laser focus and get effectively a much smaller voxel. That's how we call it, in analogy to a pixel in normal 2D printing. These are some measured foci of light. That's a whole story on its own, how we make these resists. These are not commercial resists, and some of that is still in progress. We're trying to make better resists because at the end of the day, the resolution is not limited by optics anymore. It's only limited by the resists and the mechanism in these resists. But this we have been using for a number of years. And this we also used to make these structures here, which are deep sub-wavelength. This shows you the entire Woodpile photonic crystal with this bump. It's just upside down. That's the way we make it. This is actually the gold coating here that I spoke about. And we do the optical experiments just from the other side. And for those who do care, the rod spacing of this Woodpile photonic crystal in this case is 350 nanometers. You can go down to 250 nanometer rod spacing with 800 nanometers of wavelength light. So here are some measured images. What we do is we just put it into a microscope. If you look from the kind of wrong side, you see the aberrations of this bump. Just if you care, you have this curved surface here. Light is reflected off the sides of this curved surface, and then it's not collected by the numerical aperture of the lens, and that is why you see these dark stripes. That's the interesting part. These are the optical aberrations. Forget this. This is just the edge of the structure. If you look at it from the correct side, so if this is the bump from this side here, you see these aberrations from the structure that has no cloak on it, and this is the structure that does contain the cloak, so we can make these aberrations go away. Well, big deal. Let me show you that it agrees with theory. Let me show you how this depends on wavelength. I claimed that we can make this broadband, and this is going to be important later on. I showed you images here at 700 nanometers wavelength of light. This is a typical transmission and reflection spectrum of such a photonic crystal. When you hit the Bragg resonance, big surprise, you see a dip. So we stay here on the long wavelength side, and I'm going to show you images for decreasing wavelength, and it's going to work all the way here, but eventually once you get into the photonic crystal regime, it's not working any longer. So here we start at 900 nanometers wavelength of light. The control shows these aberrations. The cloak does not. Works at 850 nanometers, 800 nanometers, 750 nanometers. Now you can see colors again. Before you couldn't see it with your eye. It's a bit dark here, 675. I hope you can see it, 650. And now at 600 you start seeing weird things here because we're running into this stop-band regime. This material does not look like an effective medium anymore. You get Bragg reflections, and then it goes totally nuts. But the good part here is it pretty much works until a point where the rod spacing is only half of the free space wavelength. I'm telling you because there have been endless discussions in the metamaterial community. How small do you really have to make the period of something that the light averages nicely over it and does not see basically multiple Bragg reflections of it? At least in this situation it's very forgiving, and you can make the spacing as large as only half of the wavelength. Some people have argued you have to make it 10 times smaller, otherwise it's never going to work. Well, in this case, this is not true.
Is it really dependent on polarization?
Good that you ask. No, it does not depend on polarization. Actually, these are images that are with circular polarization of light, because we did it with a laser. We can't depolarize that easily, so we did it with both linear polarizations and also with circular polarization, and it does work. That's important. That's not a surprise, because the Woodpile photonic crystal in the regime we use it is polarization independent in its properties and also pretty isotropic. It's just like, it looks like a stupid refractive index, which doesn't care about polarization and doesn't care about direction, etc. Was there some? Yeah.
What's Woodpile?
Oh, sorry. That's just the name for this structure. I'm sorry. Thought everybody had seen something like that. That's a name for this structure. So it starts with one layer of rods. You put a second layer of rods on top, like you staple wood in the forest. And then the third layer is actually parallel to the first, but displaced by half of the period. The fourth is displaced with respect to the second, and then you repeat. So it has 4 layers, and then it repeats itself. Actually, if you stare at it long enough, it's a diamond crystal. There's diamond symmetry if you do it right, and that's why it's nicely isotropic if you go to the center of the Brillouin zone in the long wavelength limit.
And it depends what kind of polymer you use for stacking, or?
Well, yes and no. I mean, for most polymers you would get a refractive index of the polymer itself of order 1.5, and then the result will be the same regardless of what you use. You want to use a polymer that has low absorption, obviously. That's not desired here. But apart from that, it's just a stupid dielectric, basically. You might as well do it with glass or anything else. We just happen to be able to structure polymers more easily than glass. All right. So let me do a fast forward here. So it's broadband. Here, these fundamental limitations I told you about in the beginning do not apply. So one thing we cared about is this now an invisibility cloak only for the amplitudes, or does it also do the job that I told you in the beginning, that all the optical path lengths, all the times, all the phases are the same as if you had a homogeneous medium? I've met different people. Some say it's totally obvious. If you get the amplitudes right, the phase must be right. That turns out to be wrong. There are counter examples. There are examples where you make something invisible just on the level of ray optics, but not on the level of wave optics. Just trust me, otherwise I can show you these examples. I don't want to in this case. So the experiments we have done are like follows. We take the sample, we image it onto a camera, and that's what I've shown you so far. We illuminate with a laser to make it well defined, and now comes something new. Now we let the image of the sample on the camera interfere with the image of a reference on the camera. There's just a plain mirror here. And then we move this stage like in a Michelson interferometer, and then you will get at every point of the camera interference. And this interference you can look at. Here you see some of these interference fringes. And if you track the interference fringes, you can directly infer a phase profile from that. This is not a terribly big surprise, but this is our experimental data here. So here you see the structure without the cloak, and big surprise, you see in the face simply the geometrical structure, like you would think naively. It takes less time if you hit the top of the mountain, takes more time if you hit the valley. It's just totally trivial actually once you look at it. But then with a cloak this gets fairly flat. It's not perfect. It should be absolutely flat for a perfect cloak. It's not perfectly flat. This is just a control from the other side. If you look at the cuts, this is how it looks like. The two controls coincide. For the experts, that tells you that I'm not cheating. And this is the face profile that we are basically hiding. It has a height of 3 pi, and this is what the cloak does. It brings it down by a factor of 7 or so. So it's not perfect, but it's broadband and works pretty good. So we were quite excited about these things, but you might ask, who cares? Who needs these carpet cloaks? And I was asked this question many times, and I said many times nobody needs these cloaks. It was just a scientific game until some friends pointed out to me that there are actually applications. And one of them is to make contacts, metal contacts on solar cells invisible. And the thing is the following, I guess you know this. Every solar cell, think of a silicon solar cell on your roof, has metal contacts on top, and you need them to get the current out. And you also need them because otherwise the resistance would be too high and you get ohmic losses in the solar cell. So you have to make them of a certain width, otherwise you suffer from ohmic losses. But then on the other hand, optically you do not want these contacts because they shadow part of the usable area. So when I first saw this, I said, well, who cares? It is just a few percent. Well, it turns out the solar cells on your roof have a coverage of the metal between 5 and 10%. So 5 to 10%, depending what solar cell you have bought, are wasted. You waste 10% at max of the usable area. And if somebody gives you a trick how you can nicely guide the light around the metal contact, you can increase the efficiency of the solar cell. And well, then I thought it's going to be pretty difficult to add something like that. But it turns out that solar cell industry does consider switching to new technologies, even if you give them like 0.5% absolute increase of the efficiency. So just to be clear, I'm talking about 10% max relative increase. So if you start from, say, a very good silicon solar cell that has 20% conversion efficiency, I can bring it up relative by 10%, that is to 22%. It's not a hell of a lot, but again, people in industry care about if you bring it up from 20 to 25% efficiency, absolute. Okay, so how can we do this? First of all, I should say that we are not the first to realize this problem. Many people have thought about this problem. These are some early patents. This is the earliest patent I have found, an earliest publication, where people have fabricated like this dielectric groove that refracts the light to go around the contact. This works very nicely for normal incidence. It's far from perfect for all angles. It works, but it's not perfect. People have also come up with other solutions. Just to show you something, this is a fairly recent one, actually with a company doing this, and they have made triangular metal contacts. So if this is the solar cell surface, they have given the contact such a shape that the light is reflected off the edge of the contact and reflected towards the active area. Again, this works, but it's not perfect. There is no scale on this figure, but don't blame me. There is no scale in this publication, actually. But what you can tell, it's not perfect, and we talked to the authors. They kind of solved half of the problem. They recovered half of the light that was otherwise lost. So again, it works nicely, but is not perfect. So how could you make it perfect? To go back to this transformation, if you use that, this could be a silicon wafer. This could be from here to here the metal contact. And on paper, you just perform this coordinate transformation. You get this material parameter distribution around, and then all the light would be guided around the contact nicely on the silicon wafer. But as I told you, this is never going to work broadband because of relativity. Okay. What can we do? We can do it approximately with conformal maps. And you don't have to understand this in detail, but there are other analytical transformations, like this Schwarz-Christoffel transformation, that allows you to transform a half space to a polygon. It's pretty fancy. You can look this up. This is totally well known in the mathematical literature. The beautiful thing is that in this case, after some pages of mathematics, actually you get a refractive index in a closed form. Remember, x and y are real and imaginary part of this complex number z here. So you see immediately, depending on the conditions, what this exponent is, you either get a 0 of the refractive index. That's a very bad thing, because that means the phase velocity is going to infinity. Or you get a pole of the refractive index. That's also very bad. Light will get very slow and you will get losses like crazy, but at least it's one of the very, very few cases where you get a closed analytical expression for a refractive index profile. Never mind the mathematics, that's how it looks like. So basically what we have done is we have taken this line, thought of this as this being one half space, this the other half space, and we have transformed this line into a polygon. And this is 1, 2, and the other point is at plus infinity or minus infinity here. We have transformed it to a polygon with 3 corners. And for this you get analytical solutions. You can give it 15 corners and it's still analytical. And despite all the mathematics, I think you understand this intuitively right away. This is a refractive index profile going from 1 to 1.5 again, because that's what we can make. And you see here you have a low refractive index region, so this acts like a negative lens, very naively speaking. So light is kind of refracted around here, and then here you have 2 positive lenses, so it's positively refracted here. So I think you have an intuition that light would be guided like this. This is again the silicon wafer, this is the contact, and with this geometry you would never hit the contact. Still, it's a fairly fancy structure. We have made this structure. Martin Schumann has done this 2-3 years ago in his PhD thesis. And this is a very large Woodpile photonic crystal. Again, this thing that we discussed, again used in the long wavelength limit. And I give you an idea of the refractive index profile. You can't see the layers here. There are so many. In this case, I think it's like 350 layers in this direction here, very densely spaced. And you see a silicon wafer on the bottom. This is a metal contact. I believe it's a silver contact in this case here. So the experiment we do is very simple. We take a laser focus and we scan the laser focus across this contact. And what you see is we detect the photocurrent. What you see is you get high photocurrent until you get here. Then the photocurrent drops and comes back again. Big surprise. This thing acts like a shadow. This shadows the incident light. This thing here, it goes almost all the way down to 0. And if you put this refractive index profile on top, then this deep minimum at least gets less pronounced here. This is not an artifact for those who care. This increase here comes from the fact that we reduce the reflections at the silicon-air interface by going to a silicon polymer air package. Basically, it acts like an anti-reflection coating. This is a trivial effect that this goes up here. The interesting part is that it brings up this minimum here, so we kind of gain all that light that is in here and can increase the solar cell efficiency in principle. Still, we felt this is a ridiculously complicated structure to put it on square meter levels on roofs of people. So we thought a bit harder how we can simplify this. Oh, this is actually far published by now. And the point is that the phase or the time of flight is actually irrelevant for the solar cell. You got a question?
So the solution you showed on the slide before, it still has the problem with the angle, right? If you don't have light at straight angles, it doesn't work properly.
It depends a bit how you make the structure here in the middle. If you metallize this part here, this edge, then it can come from any angle. If you do not metallize this part, then you have an issue with angle. And I will come back to the incidence angle. That's very important because for solar cells you want this to work for all angles. And the final solution is going to work for all angles.
My question was also following this one, because I can imagine that if we transfer any object to more circular shape, then the system would be more omnidirectional because the polarizability wouldn't change, right? Its sensitivity to the angle of incidence would not be very important. But the moment that we start to have all these kind of like sharp edges and complicated shape, when light sees different cross sections, right? Therefore, the response should be very different.
Well, once again, the transformation would bring this ground plane, this metallized layer, to this metallized layer. And if you do it like that, it's just fine. Yeah? Regardless of all these angles here. Actually, you don't need all these angles. These kinks, if you want, are nice mathematically, because then you can do it analytically, because you have these piecewise straight solutions. But apart from that, actually you might as well round this off. I think that's the direction you are thinking at, to make this rounder. That's a possibility. You're going to have a harder time with the mathematics. You can't do anything analytically then. At the end of the day, it's going to look more or less the same. But the problem with the omnidirectionality has nothing to do with these edges here. This has really something to do with what boundary conditions you put here. If you have refractive index boundary conditions, this is going to be imperfect for oblique incidence if a light ray comes like that. If these are metallized boundary conditions, then it's exact. But this is a pain in the neck to make. The bottom line will be, forget this structure anyway. This is just our historic path, how we got there. So this will also give you the same time of light from somewhere to this silicon surface as if you have had nothing of this stuff here. This will give you the proper optical path length. But who cares about that? In a solar cell, you just want the light to get on the active area, and nobody cares when it hits the active area. So this allows you to do other things, and this is, I think, a nice little trick. I'm using this coordinate transformation that I showed you a couple of times already. And what we want is, this is kind of a side view onto the solar cell. This would be the silicon surface. This is our contact here again. What you want is that light rays that hit, say, the contact here magically get expelled from this region. So what you want is that there's some magic, that this light ray is not hitting the contact, but rather that you expel this part here from space, and that this light ray is mapped to this point here, where you again have active area of the silicon surface. This is what this transformation means. We again take a point, we open it to a finite interval, and we put the contact in the interval, and then no light will ever hit the contact. That's the simple idea. But how would anybody do this? Why would light be refracted at this interface here? Well, there are different opportunities. You can put these fancy meta surfaces, if you have heard about this stuff. Structures that give you a phase jump at the surface that allow you to get anomalous refraction. But you can do it much simpler. You can say, I use a local inclination angle here. I tilt the surface at this point, and I tilt the surface such that I get a certain angle alpha, such that I exactly get this coordinate transformation. You basically map the coordinate transformation onto a curved surface, onto a free-form surface. And then you have to go through the mathematics. You can read off the angle alpha. The tangent of alpha is given by this thing here. This is x prime minus x divided by the height of this thing. And if you stick in, that's basically this first part here, then you can get the local inclination angle here of the surface. I've called it beta, and put Snell's law. This is just solved for beta. And then you can integrate beta. If you integrate the tangent, you basically get the height. But the problem with that is that you kind of run in loops, if you see it here. You need to know the height to get beta. If you know beta, you get the height, and then you go again and again. But you can solve this iteratively, or you do it numerically right away. You can solve this. You can also solve it analytically with some approximations, but better you don't do any approximations, and solve it on the computer, and that's what you get. You get basically a surface. It's just that the height here varies as a function of the coordinate, and the purpose is that if a light ray comes in here, would otherwise hit the metal contact is now refracted at this interface towards the silicon surface. And the way this transformation works is that it actually redistributes all the light evenly over the remaining area. So some people like to call a structure like this a lens. I don't think one should call this a lens because it is not a lens. A lens to me is something that maps parallel light rays onto a point. This thing does something different. It maps parallel light rays such that they avoid this region and distributes them equally over the remaining region. So if you wish, call it a lens, but I think it's incorrect. This is not a lens. This is just some freeform surface, and this is actually the structure that we have fabricated by this direct laser writing technology that I showed you. There are a few tricks, if you care, that we have used to accomplish this. So does it work? Again, this test, we use a laser over the reference structure. You see the shadow. The current goes almost all the way down to 0. And then for the cloaking structure, again, you have this impedance matching story that's trivial but nice. And then you have only this little glitch left here. So here we have gained actually even more than with the fancy structure that I showed you before, this graded index structure. So now back to the question of oblique angles of incidence. This shows you some ray tracing calculations for normal incidence, and I think I explained this a lot already. And this is for oblique incidence, just an example, 40 degrees angles. And you can go up to higher angles. The way the structure works is that whatever the direction is, the light rays are always refracted away from the contact. They never hit the contact. That's an exact statement for all angles of incidence, if you care, up to a filling fraction of the metal on the surface of 20%. So for 10%, which is less, you can do it exactly with this kind of a solution. You can recover all the lost light, at least on paper. Okay, never mind these details. Let me get away from this. Let me show you something more recent.
Question.
Yes?
Why don't you call them lenses? I still don't understand the difference, because if you, for me, they're still like micro lenses, but with the edges right on the metal surface.
Yeah.
I mean, if I think about my master's lecture by Professor Kant, who's also at the same university, then I remember such structures where you can avoid reflection because any light at different angle would always look at the surface at normal incidence.
The reason I don't call it a lens is because it is not a lens. If I use a special case of this transformation, that all the parallel light rays cross in one point on the silicon surface, then it's a lens. It's a cylindrical lens. But here if you look at this as the image plane, they don't cross in one point. They're simply not mapped onto a point. They are rather evenly distributed. It's a curved surface. If your attitude is you call any curved surface a lens, I'm fine with that. But usually we are a bit more specific in optics, and a lens, a focusing lens, to me is an object that maps parallel light rays onto a point in the focal plane. And this thing does not do this.
Okay, so that's the reason that you did.
Yes, but I don't want to debate with you about the name. I'm just mentioning this. I don't call this a lens because to my understanding it is not a lens. It's a curved surface, but with a very special shape, not some parabolic or spherical shape, right? It's a very weird shape. So we've made this by this 3D laser printing, and still it's very difficult to imagine how you would make square meters of that stuff. But this is going in this direction. So what Martin Schumann has done here is we have made a master, and then we use this master for soft imprinting. I tend to call it stamping to make it distinct from the other type of printing we are doing. So we make the master and then we simply stamp it. We are not the world leaders in stamping or soft imprinting, but we have improvised something here. And this is the result. This is a silicon solar cell. It's a bit dirty, but otherwise the state-of-the-art silicon solar cell that we got from some collaborators at Jülich. You see the silicon surface, that's the silicon surface here, and you see the metal on top, one of these fat bus bars, and then you have these metal contacts here to the side. That's how they look. And here on 5 of these metal contacts we've put our cloaking structure, 1, 2, 3, 4, 5. And what you can see is that actually you don't see the contact. Believe me, it was like that before, that on the left and the right you have a contact. You don't see that contact here. And what you see is actually good. A solar cell should look black. It shouldn't have any color or anything. It should absorb all the light. And in fact, this is in a way the same that I showed you before. By putting this structure on top, it's getting blacker than it was before. We make it better. We make it more absorbing. Okay, that's a good thing here. And it's kind of cool that you can look at it and you don't see the contact anymore. So it's not cheating. They are invisible. And if you don't care about pictures but rather about data, this is showing you the current voltage characteristic of one of these solar cells in a solar simulator. So far I showed you experiments at single wavelengths and partly at weird wavelengths that we used for historic reasons. This is in a normal certified solar simulator that gives you the entire visible spectrum like the solar spectrum. And you can see that the short circuit current is going up from the flat polymer here to the cloak by this amount, which is not a humongous amount, but I told you we are expecting at most like 10% relative increase. And this brings us to the question of angular response. This is now showing the relative improvement here as calculated and as measured, and you see up to about 60 degrees angle of incidence with respect to the surface normal. It's just flat and within error what you expect theoretically, and then it goes up, becomes even higher. This is a bit weird. It took me a long time to understand this. If you take only what I told you so far, this should not happen. This happens because you have also reflections at this interface. And what happens is that the light is refracted towards the silicon surface, then maybe reflected from the silicon surface, but then it comes under such odd angles that it's kind of trapped in this weird shape there, and it acts like a trapping layer. This is luck. This has nothing to do with our coordinate transformation, but it's good because it further increases the efficiency. But actually, for the annual average, this part plays no role. If you look what contributes really to your average energy conversion, only light rays to about 60% or so. 60 degrees are relevant. But it works even beyond. And weirdly enough, it even gets better for larger angles of incidence. So that's where we stand. In principle, you can mass fabricate these things, make contacts invisible, and increase the conversion efficiency by that. But you had a question.
Yeah, in the previous slide.
Yep.
So you do see these white stripes, but
yes.
They seem displaced. So is this some kind of weird image of the original rods? Or
I don't know what you're talking about. What do you mean?
The black part is the part where you stamped it, right?
Yes.
And then you have the whitish.
There's a bit of a spacing between.
That's
stamped it once, stamped it twice, wasn't exactly the right width here.
Okay.
Yeah, there's just a space between these two structures. You see the bare silicon surface like here in between these.
Related to that, why not cover the whole thing, the material, and just make the dents, I'm calling them dents, where the refractive index profile is like this structure only at the contacts, and cover the whole area with this?
Yeah, this is just a fabrication issue. That's the way we did it. We did one master and then we stamped 1, 2, 3, 4, 5 times. This is by far not perfect imprinting, but people have imprinting under control, and if we can do it, everybody can do it. The issue is rather in making the master ones, because I don't know of any other technology that would allow you to make these weird shapes. And actually, more and more people get these kind of ideas that by 3D laser printing, you can make all kinds of freeform surfaces and then print them to make them in masses. I'm just not allowed to tell you where you will soon find this in products. In many instances in optics, you actually want all the design freedom to get freeform surfaces. This I can tell you, for example, in these Google glasses, or Zeiss is also making these glasses where you project something onto your retina. You don't get away with spherical surfaces. You need very strange surfaces, and that's one way how you can make them in arbitrary form. It's nothing to do with coordinate transformations, but this is a bit more general. All right, so this is the just the first file here. Let me go to the second file and speak a bit about thermodynamics. So we have 15 minutes to go, and then we make a break. And there's a switch of gear. And I first want to show you something about heat conduction. Going very far away from optics, but then we will come back to optics as it turns out. So when I say thermodynamics, I speak of heat conduction and particle diffusion. In both cases, the entropy rises. So remember what I told you in the beginning. If you want to use these tricks of coordinate transformations, first thing you have to check is, are the equations that you want to work with form invariant under coordinate transformations or not? And this is the usual heat conduction equation. You have the divergence of the heat conductivity times the temperature gradient minus the specific heat times the temporal derivative of the temperature, and this is 0. Just the continuity equation for energy, basically. And this equation is form invariant, as was shown in this paper here, actually not so long ago, by my friend Sébastien Gounod in Marseille. Not a big surprise in retrospective. The spatial part of this equation looks pretty much the same as a wave equation. It's also a second order derivative with respect to spatial coordinate. It's just that the temporal part looks very different from a wave equation. In a wave equation you have the second temporal derivative here. In diffusion or heat conduction you have the first temporal derivative. But if you have actually understood things, it doesn't play a big role because we're transforming the spatial coordinates only anyway, and we're not doing a temporal transformation. So we're not directly affecting this part here anyway. So this is form invariant, and so is the diffusion equation. There is a difference, just if you care. So in the heat conduction equation you have two parameters. You have the heat conductivity and the specific heat, whereas in the diffusion equation you only have one parameter, and that is the diffusivity. There is no counterpart of the specific heat in diffusion problems. But if you consider the static case, then they are actually strictly equivalent. That's what I told you before in this huge overview view graph. So let's play some games with thermal cloaking. And here I use now this transformation from a point to a circle that I mentioned so many times. So we start with this point here, we open it up to a finite circle, and in the surrounding we get this anisotropic distribution of the heat conductivity. And you can work this out mathematically and then map this onto a microstructure, or it's actually a millistructure. The dimensions are given here. This entire thing is like this big or so. So what we do is we get the anisotropy that is required by this lamination. So we have alternating rings of high and low heat conductivity in this experiment. The rings give you the anisotropy, so this is kappa and PDMS in alternating form here. The kappa is a very good heat conductor, so you get good heat conduction in the azimuthal direction, that is around the circle, whereas you get very bad heat conduction if you have to go through the PDMS layer here, if you have to go normal to this laminate. I guess this is one of the oldest metamaterials that is around. You know that in transformers also these stacked systems are used where you have a thin sheet of a conductor, electric conductor, you have a thin sheet of an isolator, conductor, isolator. So this is well conducting in the plane of the sheets, but very isolating in the normal direction. And this is used for ages to prevent eddy currents. But lately has seen some reincarnation in the form of hyperbolic metamaterials, which are pretty much exactly the same thing. Also layered systems of metal isolator, etc. Just in case you've seen this. So that's how we get the anisotropy. And then by this perforation you see here, we do this grading. I mean, it's supposed to be a continuous transition. And here we mimic this, I think, by 10 concentric rings. That's actually the structure. You have PDMS in here. And maybe you can guess that because the kappa part is not falling down. So I'm not cheating you, there's actually PDMS in here and you just don't see the background. So the purpose of this structure is to guide heat around the center. You will hence keep the center cool, you will prevent it from overheating, and the surrounding doesn't see any of this distortion because the way we do it. To the outside world it will look like a homogeneous plate, in this case homogeneously perforated plate. The heat will be guided around and it will look like if you had a homogeneous plate. And the experiment is very simple. We let heat flow from a hot bath to a cold bath. We monitor this with an infrared heat camera. We actually take movies how the heat is transferred here. And I'm actually not sure which pictures I have in this talk. I think I have some images in here. Maybe we go through this here. There's a common misunderstanding I have encountered, that people think cloaking is the same thing than isolation, than isolating something, and that is not the case. So for those of you who are in optics this could be a light wave and it goes plus minus, the electric field is positive, negative, you all know this. This is different in thermodynamics. There we talk about temperature or density. These are positive definite quantities. So it's all positive. It's just smearing out its entropy increase. But you can make it look a bit more the same by adding these iso temperature or iso density lines to the picture. And these iso temperature lines somewhat resemble the wavefronts of a wave. I say this with a warning. There's lots of nonsense you read in the literature about heat waves in this context. There are no waves in the heat conduction equation. It's just smearing of things. But that's how it looks. Now if you only isolate something, I put a metal wall around me, you won't see me anymore, but you see the metal wall pretty obviously. In other words, the light wave is getting scattered off the object, say off a metal wall, and you will get diffraction and all kinds of weird effects. And it's a bit similar in thermodynamics if I put some styrofoam isolation around me and then look at the temperature field around me. You see these distortions. It's no longer straight lines. And these isotemperature lines actually look a bit like the wavefronts in optics, for example. I'm not saying it's the same, but I'm saying there are some analogies. But obviously, this is not cloaking. This is isolating an object, but to the outside you would see that there is something. You wouldn't see me, but you would see the metal wall around me. So here you see some calculations of the simple isolation and the cloak. Let me just go forward. And here you see this distorted temperature profile, and here you already see that on the downstream side the heat has arrived and you get a straight vertical temperature front, and this just continues in the theory. And now you see the same thing as measured. Again, I'm comparing the simple isolation and the cloak, and you see that here we are already pretty much recovering a straight isotemperature line, whereas here things are curved on the left-hand side. And you also see that the center stays cool. And this is a combination of different images of the photograph and of the measured temperature profile that you get a feeling for what these wiggles are, which are first thought were noise. They are not noise. So red means warm, blue means cold. This is measured, and the whole point is that this downstream isotemperature curve just outside of the cloak is again a straight line. We have recovered the same situation as if you have nothing in the middle, as if you have a homogeneous medium. And in between, of course, heat is guided around, and these wiggles kind of mean that you look into the unit cell of the metamaterial if you want to hype it up. You can basically see that the copper here conducts the heat better than the PDMS isolation, and you can even see these little things here in the temperature profiles. So this works kind of nicely. Now, you can do the same thing as in heat conduction in diffusion, and you might do this for diffusion of massive particles. somehow I couldn't excite myself about that. But then we reminded ourselves that there is a regime of optics in which you can describe light propagation by a diffusion equation. And this is the case in fog or in clouds. This is the case in milk, in eggshells, or in frosted glass, whatever. Like the wall here, this wall doesn't reflect the light ballistically, it diffusively scatters the light. And in fact, if you want to describe this wall here optically, you would have to say that the diffusion constant or the diffusivity of light at this wall is close to zero, and that's why everything is diffusively backscattered. This would be an example of close to zero diffusivity of light, this white wall here. So if we can use this analogy, then you can copy all the tricks that I showed you so far to diffusive light propagation. Maybe I finish this introductory part and then we make a little break. So just for those of you who are not working with diffuse light scattering every day, let me remind you of some totally well-known things. So in a diffusive medium, you have scattering particles. Can be water droplets, can be anything, can be molecules. And a very important quantity is the scattering mean free path length. It's basically the average distance between subsequent scattering events. And it scales like 1 over the density of scattering centers and like 1 over the scattering cross-section of the individual centers. Here I'm assuming they're all the same, right? So you can control the scattering mean free path length, say, by the density of scattering centers. And now you have to compare the scattering mean free path length, or better, the transport mean free path length. They're not exactly the same. They're proportional. If you care, ask me. You have to compare this mean free path length with other quantities of your problem. You have to compare it with your system size, and you have to compare it with the wavelength. So if your mean free path length becomes comparable to or even larger than your system size, then you go back to ballistic transport. You go back to Maxwell equation type of optics on this side here. Then you cannot describe it by diffusion. You're back to Maxwell's equation for continua, of course. If your scattering mean free path length becomes very, very short, that it's comparable to the wavelength of light, then you eventually get into the regime of light localization. People have looked at that for years and years and years. It's actually very hard to get into this regime, because what very often happens is before you see this regime, you see some absorption. And that's because if your background medium has some teeny, tiny, but non-zero absorption, then all these scattering events basically give you a much longer propagation length in the system. So effectively you pick up small absorption coefficients because of this huge propagation length. And this you see at some point. Never mind this expression, but you do see it at some point. The reason I'm telling you is that the diffusivity, or it's like the conductivity for light actually, is simply proportional to the mean free path. So if you have very low concentration of scattering centers, the mean free path is large and the diffusivity is large, and vice versa. So what this all means is that by playing with the concentration of scattering centers, I can adjust the diffusivity, but I cannot go to infinity. Then I go back to ballistic optics. And I cannot go to zero diffusivity either, because then you would go into localization or absorption. But there is a huge interval in which you can play. This is just a scheme. I would say that this can be a range of 3 to 4 orders of magnitude in which you can play with the diffusivity of light before getting into trouble in the sense of violating the assumptions you have made or getting absorption or something like that. So you can play with the diffusivity a lot, say with a factor of 1,000, and this is a much better thing than in ballistic optics. If I could play with the refractive index, which is kind of the counterpart, by a factor of 1,000 without invoking resonances, I would be a famous man. Then you can do fantastic things in optics. Unfortunately, there are no materials like that. And because the contrast is so much larger in the diffuse regime of light propagation, I will show you I can do things that you cannot do in ballistic optics. And maybe we do that after the break. So here I showed you a minute ago heat conduction, and now we're switching here to particle diffusion, light diffusion, that is. And the question we have asked ourselves is, do you really need all these layers? I mean, ideally, if you do this coordinate transformations, you need many of these laminate layers. High, low, conductivity or diffusivity, or whatever you care about. But you might ask yourself, well, do I get away with fewer and fewer layers? And the absolute limit to me would be to use only 2 layers. One with high diffusivity in my case, and one with low diffusivity. This sounds like a total brute force approximation, but it turns out it works amazingly well in this regime. It's amazing. And this was pointed out by this gentleman here, Kerner, a long time ago, more than half a century ago. And this gentleman was also aware of the fact that all these problems are mathematically equivalent, what I emphasized also. This is not new. This guy was aware of it. There's only one problem. The words that he used cannot be Googled easily. Today, a fashionable word would be to speak about core shell structures. Plays also a role in plasmonics. Some of you are in plasmonics, I understand. He called it coated grains, so you cannot Google core shell, but that's exactly what it is. It's exactly that. And he covered actually so many cases that you have to look a moment to find the special case that corresponds to cloaking. But it's all in his paper here from 1956. It's really amazing. Let me show you a magnetic counterpart just for a refreshment. I mentioned that all these cases are equivalent. You can also do this in magnetostatics. Then the analog is the magnetic permeability. And this is a nice experiment by a Spanish group. So what they did is they considered this core shell structure. And the core, in their case, is a superconductor with, as you know, 0 magnetic permeability. It's an ideal diamagnet, which means mu equals 0. That's the core. And then they put this shell around, which is a ferromagnet that has a higher magnetic permeability than the vacuum around, which has mu equal to 1. And what they showed is that this thing, of course, the superconductor expels the field lines. They cannot go through, but you will get a distorted distribution of magnetic field lines. And then this shell, the ferromagnet, makes it appear again exactly as if nothing was there. It's a very nice experiment that they did, and they scanned a probe here across this thing and actually measured the magnetic field. I don't have their data. This was published in 2012. I'm showing you this to make the point that the wall here with close to 0 diffusivity is actually the counterpart of a superconductor. Plays the role of a superconductor. Or for those of you who are maybe in plasmonics, it's also equivalent to an epsilon near 0 material or metamaterial. We're getting very small diffusivities. And that's what we do. If you just put an isolation, this would be a near 0 diffusivity hollow cylinder, then of course light is somehow guided around. This again isolation. And if you put this additional shell here, that it becomes a core shell structure, and the shell has to have the right thickness and the right concentration of scattering particles, then you can show on a piece of paper exactly analytically that the light is guided around as if nothing was there, as if this was a homogeneous medium. This is an exact statement, and this was shown by Kerner in 1956. When I draw these lines, I mean, of course, lines of the, these are the streamlines of the current density of photons. Microscopically, you have all these scattering events. This would be the average current flow, photon current flow that I'm showing you here. And you can do this in cylindrical geometry, and you can also do it in spherical geometry. Yes?
Does it depend on R1? Can it be arbitrarily large or small?
Yes, it does. This is the closed formula that you get, how the diffusivities have to look. Of course, it depends on R1, but if you take an example here, it's actually quite forgiving. If your outer radius is 25% larger than the inner radius, that's what this means, then you get a contrast in diffusivities of this factor. The contrast will explode if you make the shell, relatively speaking, thinner and thinner. Then it will go sky high, but 25% is thin enough for my taste. Does this answer your question? I mean, the absolute size doesn't matter. What matters is only the relative size of R1 to R2. Absolute sizes are irrelevant here, as long as all these other conditions I mentioned in the beginning are fulfilled, that you are still in the diffusive regime. So this is an early experiment, just a game actually that we played. We did is we used a metal cylinder, a hollow metal cylinder. So this kind of isolates the space inside from the outside. We coated this metal cylinder with white paint, white wall paint, which gives you close to zero diffusivity for light. And then we have this PDMS, one of our favorite materials, this transparent rubber, a thin shell around that we have doped with dielectric particles at some suitable concentration. And then we decided to start with water with white paint in the surrounding, to be honest with you, because we wanted to be able to play around easily with the concentration of scattering particles. You don't have to make one sample and then you see it doesn't work. Here you can just pour white paint into the surrounding until it works actually. So it's very easy to change concentration, easy to change the diffusivity. So normally this thing is filled all the way to the neck here. It's just a water tank. Just for illustration, we have filled it only half. And then the experiment is outrageously simple. We illuminate actually with a monitor, with a computer monitor from the back. That's what you see here, this white area. And we look at the front. And we use the computer monitor because you can use all kinds of patterns, lighting, illumination patterns. You can program different colors very easily. It's just very nice. And here you see some results. This is for reference what you see in air. This is totally unsurprising. You just look at a bright monitor. If you now put one of these cylinders in front, it will cast a shadow. This is quite trivial. So this cloak does not work under ballistic conditions, but under diffusive conditions it does. So here you look now at the computer monitor through the diffusive medium. It looks a little yellowish because the blue colors are scattered more. This is roughly in the Rayleigh scattering regime, and hence they are missing here. This is illumination with white light. And now you put this isolating cylinder in front and you see a shadow. This shadow is diffusively broadened compared to a normal shadow, but this is not surprising. And now we put the core shell structure, that is the cloak, and we go from, say, a factor of 4 or so contrast here to these 10% wiggles. This is what we got in this paper. And I emphasize that this is a macroscopic object. This cylinder is a couple of centimeters in size, 5 orders of magnitude larger than the wavelength. We're looking at all visible colors here. And due to the geometry, you can look at it from all angles you want, and polarization doesn't play a role either. So here this fundamental limitation I showed you in the beginning for ballistic light propagation does not apply for diffusive light propagation. You might ask, well, but this is only for homogeneous illumination. How does it work for other illuminations? This is one example. If I just illuminate a stripe, then in ballistic optics you don't see anything. You're just in the shadow of this thing. Then in the diffusive regime, this stripe illumination is getting broadened diffusively. No surprise so far. Then if you just put the obstacle, the isolating cylinder, then the effect is even bigger. You decrease the intensity. These are always cuts through the middle here of the structure by about a factor of 10. And then with the cloak, you pretty much recover what we had here. I should say that these images are, of course, shown on the same scale here. Otherwise, I would be cheating you. So you should compare this with this. And to me, this is pretty good. It's not perfect, but it's pretty much recovering what we had. And you can also do the same thing in a spherical geometry, just in case. So reference, you see the shadow here, it's less pronounced, and then the cloak makes the shadow go away. So macroscopic, broadband, all angle, all polarization cloaking is possible in the diffusive regime of light propagation. This is just another case. Then this is a sphere with some disk-like illumination. Never mind. Who cares? Who needs such a cloak? Well, the first thing is not so serious. This is just to illustrate the geometry. So if you have a bathroom and you don't want people to look into your bathroom, you may want to use some frosted glass on the window. Here I'm not talking about frosted glass in the sense of a surface corrugation. I'm talking about frosted glass that has scattering centers in the volume of the glass. And then you may also want some protection against people breaking into your room. And you may want to have some metal bars in front or actually in the glass. And then even though you have this nice and fancy bathroom, you may have the impression that you sit in a prison cell. And if you want to avoid this, you can put this shell around the metal bar and it will disappear. This is a fake. This is the computer solution for our experiment faked into this photograph. This is not a real thing, but you might as well do this. This is just to illustrate the geometry. We have a back illumination. So for any back illumination situation where you have something in the way that you want to make invisible, this geometry works. Aha. Something more serious is maybe this thing here, and this was brought to us by our friends from electrical engineering. Uli Lemmer's group is an application for OLED wallpaper. So organic light emitting diode wallpaper. Just in case you haven't heard this, these people are dreaming about wallpaper that covers square meters of your room that is light emitting. And this is coming up. You can buy from Osram panels that are this size here, and you can put them on your wall and make your entire wall light emitting. There's only one issue. I have faked this into this thing here, and that is again that you need contacts on the surface. The sheet conductivity of these organic layers is so low that if you don't put metal contacts, the ohmic resistance makes the emission totally inhomogeneous. So all these commercial products have usually hexagonal grids of contacts on top to bring the conductivity up. But then you see these contacts again, which somehow industry and people don't want. They want a homogeneously emitting surface and not some structured surface. Damn it, I have forgotten to put the view graph in. So what you can do is, if you have this surface and you have the contacts on top, you can put a structure on top of the contacts and again make the contacts invisible. It's not exactly the same as the core shell structure. It's a different triangular solution that we have come up with, but you can make the contacts on the front side of the OLED invisible in the sense that you see a perfectly homogeneous light emission. At least on paper you can do it exactly. In the experiment you can do it pretty nicely. It's not perfect, but it's pretty nice. Sorry, I forgot to put the latest view graphs in here. This was published in 2016, spring or so, 2016. So let me make a little... Oh, yes.
Yeah, I have one question about the core shell. So the cloaking basically happens right after your object, if it's called correctly, because I was just because I'm not from optics, so I'm all having very simple thoughts.
Yes.
So when I saw here and you put water and white color, I was just thinking when I drop my cookie into my glass of milk, at a certain point I also don't see my cookie anymore, right? But so here I was wondering, so the cloaking basically is independent of the distance between where I'm looking and...
Yes, in particular you here this distance is very small.
Yeah, so that one I can make.
Yes, so your cookie you would still see under these conditions. If you go very far away from your cookie, of course you don't see the cookie. This is kind of trivial, so this we wouldn't bother about. But that's the same in ballistic optics. If the object is very, very far away from you, you don't see it. Right? So it's getting impressive if you're close to the object.
So, and before we saw some wiggling. So how is it here in the diffusive case? So how close could you actually make it? Especially when you're talking about OLED wallpapers, you don't want something to be like, let's say, in the centimeter region.
Yes, you want this to be thin. So mathematically, this works directly outside of the shell. You have to go epsilon out of the shell and it works. In the experiment, of course, you have to go at least a few mean free path lengths away. Otherwise, this distance violates the assumption that the diffusion equation is valid. But this is very thin. So in practice, you can make this a few hundred microns in thickness. Sorry that I don't have the OLED thing. What industry does already is they put a thin layer on top with scattering particles in. And that decreases the visibility in the same sense as you don't see your cookie in your milk, but still you see it. You could make it totally invisible, but then you have to make it really fat. And this is unattractive. With this cloaking structure, you can make it on paper perfectly invisible with a finite thickness. That is comparable, roughly factor 2 or so, to the width of your wire. It scales with the width of your wire. The wider it is, the thicker it has to be. Oh, yes?
Maybe a stupid question, but how is the case of the OLED different from the solar cell? Are we considering diffusive light in case of the OLED?
How is the OLED case different from the solar cell? Actually, we asked ourselves the same question. So if you put the solar cell cloak, I showed you before, onto the OLED, it doesn't work at all.
Because it will be absorbed.
No, it has nothing to do with absorption. It has to do with the distribution of angles. There's actually a subtle point. If you remember this surface that I showed you, and parallel light rays were mapped onto some angle distribution on the silicon surface. But what you want here is that a Lambertian emitter, Lambertian angle distribution, is mapped onto a homogeneous emission, say in normal direction. But that's not a Lambertian distribution you get if you invert the solar cell. I mean, there my rays were going like this and like this. I can invert the ray direction, but the angles are all wrong. So actually, it makes it even worse. It's terrible. It's a horror kind of thing. It does not work at all because it's not made for a diffusive light emitter. But we had the same idea. We also thought it should work, but it doesn't. You can modify this idea. That's something we are working at the moment. Have a different design principle for the OLED, and again map this onto a freeform surface, and it looks roughly similar, but behaves quite differently. It is actually different, has a different height and different angles, etc. And this works reasonably nicely. So this is an alternative to this kind of structure. So let's see, how are we doing? Let me make a little detour here. Suppose you don't care about cloaking at all. Could be. Why would you care? Because it is connected to the so-called Calderon tomography problem. I had never heard about this problem before until a few years. Calderon is a very famous Argentinian mathematician, this gentleman here, and he formulated a problem. And it refers to tomography. Just to remind you, you all have seen tomography in the form of X-ray tomography in a hospital, or in this more weird form of electric impedance tomography. The general motto in tomography is you want to learn something about the inside, say a body, from measurements on the outside. Now, the problem that Calderon formulated is the solution unique? When I first heard this, I thought, well, it better be unique. People are selling me X-ray tomography machines for I don't know what amount. People are using this electric impedance tomography on humans. It's a bit weird, but also in geophysics, you can buy these things. I mean, come on, it better be unique. Otherwise they have a problem. And just to be clear, he was not talking about some noise imperfections or incomplete measurements. He's of course assuming you have perfect data, no noise, every measurement that is possible on the outside. Can you, in principle, uniquely infer the inside? And it was proven mathematically by these gentlemen, Greenleaf, Lassers and Ullmann, that the solution is not unique. I'm lucky that I'm not working in tomography. I would consider this a serious problem. And let me try to illustrate this. And it's again connected with cloaking. So it's a mathematical proof that they present with lemmas and blah, blah, blah. And frankly, I never understood it. And I thought about it and came up with this simple picture here. And this I understand. So take this network of resistors, they're all the same, all resistors are the same, as a model system for a homogeneous and isotropic conductor. And every crystal is also granular if you look microscopically. This is a bit bigger, it's a metamaterial made of resistors if you want to hype it up. It's a very simple network and you can measure the resistance between this point and pick any pair of points and you measure the resistance. Okay, fine. Now I do the following. I do a coordinate transformation, and you are used to that already. I'm again transforming a point to a circle, and I'm intentionally doing this a couple of times. And you may realize that the resistors don't change. Also the connections between the resistors do not change. And because of that, of course, you will measure the same resistance between this point and say this point in this configuration and in this configuration. All the resistors are the same, they are connected the same way. Why would you get a different result? It's just the same network, but it's arranged differently. In this case, you have this hole, you have this void in the middle, and obviously these two distributions are different. This corresponds to a constant electric conductivity, homogeneous and isotropic, but this does not. This corresponds to a distribution of the conductivity, because here in this region you have more resistors now in parallel leading to current conduction in this direction. So the azimuthal component of the conductivity tensor in this direction here is larger, and in this direction, in the radial direction, you have more resistors in serial, so here the conductivity is lower. This is not isotropic. This is a totally different distribution of the conductivity in space than this one, yet both of them give you the same result on the outside. So their work was kind of a precursor for cloaking by showing that actually infinitely many different configurations on the inside can lead to exactly the same outside result if you allow for anisotropic properties. And they proved this for electric conductivity, but because of the analogy to all the other areas of physics, it applies to all these other areas as well. All right. So this is an issue. This was some paper we dug out. This is some apparatus that people have come up with to inspect female human breasts for cancer by diffuse light scattering. And they have all kinds of lasers, I think 10 lasers that are coupled by these multimode fibers, and then all these detector ports to look at what comes out at these detector ports, and they are trying to infer the inside of the human breast. But it's not unique. Maybe under some assumptions they can get reasonable results, but it is definitely not unique. Many different insights can give you the same measurement result. Let me forget a few things here. I'm sorry. And maybe show you this as the last optical thing. Forget all that. Let me show you a later generation of samples. So lately we got away from this water, white paint mixture thing and made a solid out of it. And the way we do it is again using PDMS, this transparent rubber, as kind of a host matrix. It's transparent, as you can see here. This is macroscopic, this thing. This is like this size here, this and this square. Then we dope it with titania nanoparticles. I forget what, I think it's 200 nanometers or so diameter. Titania is a very good scatterer at low absorption, that's well known. And then we can have this core with very low diffusivity. It's a ceramic core actually. And then we can make this core shell structure. And this system has a much better performance in terms of absorption. The absorption is much, much lower. And you can see this in this photograph. This is Robert Chitney, who did his PhD thesis on things like that. Here you see the structure. It's illuminated from the back by white light diodes. And here you see the diffusive shadow of the cylinder in the middle. And here you see that you don't see the diffusive shadow anymore. And you can see maybe that I'm not cheating. Here's the cylinder, and then you may be able to guess that there is this shell around. So with this kind of a contrast, you don't see any imperfection. It's not perfect. If you look at cuts, there's like a 1% deviation with respect to the reference, but it's getting pretty cool. And that's also the kind of homogeneity you can hope for from the OLED wallpaper kind of thing. You can make a contact. This would be the contact here. Invisible in this sense that I'm defining. For visible light, all polarizations, blah, blah. Macroscopic structures. And I would like to forget about all this and rather spend my remaining half hour telling you a bit about mechanics. And I was asked in the break about earthquakes. I hope I make it to the earthquakes. So, mechanics. When we got into this, to be honest with you, I was under the impression that mechanics is totally trivial. That's the kind of stuff I'm telling to students, I thought, in the first semester of the physics course. It's about Newton's law and Hooke's law, and it's all totally trivial, I thought. I take that back. Actually, that is the most demanding case that I have seen of all. So why is that? This linear elasticity equation at first sight looks pretty much the same as the electrostatic equation, except that there are these little tensor symbols on top here. Turns out that if you have a homogeneous and isotropic dielectric, you can describe it by a number, by epsilon. It's not a matrix, it's a number, it's a scalar. If you have a homogeneous and isotropic elastic mechanical solid, you cannot describe it by a number. You must describe it by the elasticity tensor. In the simplest case, it has only two independent components, but it's a tensor. It's a rank 4 tensor. So, first thing I would like to let you know, this equation, in contrast to all the other equations, is not form invariant under coordinate transformations. This is something that was proven in the year 2006 by Graham Milton. You can try it yourself. If you insert a coordinate transformation, you get additive terms. You can never bring it back into this form. It's not form invariant. So this is kind of game over. Means cannot build mechanical cloaks. Or the tomography problem is unique for mechanics. Well, I should refine this statement. It's not form invariant for the elasticity tensors of ordinary materials, whatever that exactly means. What you read in textbooks, ordinary materials are. So maybe a bit more intuitively, why is mechanics so much richer than, say, optics and other areas? It's because in mechanics, you pretty much always have two transverse polarizations and a longitudinal polarization at the same time. So in optics and electromagnetisms, except for few cases, electromagnetic waves are transverse. It's polarized transverse to the propagation direction. In acoustics, when you hear me now, it's exclusively a longitudinal wave that you're hearing. But in elastic solids, you always have transverse and longitudinal waves at the same time, and that makes it much more demanding. Because if you think of cloaking, you have to do it right for these 3 polarizations now all of a sudden. And this is what Graham Milton has proven doesn't work. Okay, let's go home. Or you try to find ways around this. And the sorry, I'd like to cut this. Let's talk about a simple case, namely mechanical waves in thin plates or in membranes. Or it's also the same at the surface of a body, say on the surface of the Earth. Let's talk about a plate. If you have a plate or a membrane, it's simpler in the sense that you only have one mode. Basically, the plate can bend up or bend down. It's almost like a transverse polarization can propagate in the plane but go up and down. Technically, it's not transverse, it's a flexural wave. That's the correct word. Can bend up or down, and if the plate is thin enough, that's the only polarization degree of freedom that there is. And because you have suppressed 2 of the 3 polarizations, it turns out that the equations for waves in a plate are form invariant again. Okay, so in plates or on surfaces, you can play the same tricks. So you can start from this coordinate transformation that you've seen so many times. I open a point to a finite circle. I get this anisotropic distribution of material around. And now we do this in mechanics. Forget this. And I'm doing the same trick as I showed you for the thermal conduction. I'm using these ring structures, high and low conductivity then. Now it has to be fast, slow, fast, slow, fast, slow wave propagation to get the anisotropy. So the issue is to get materials with a sufficient contrast. And here we have picked a plastic, a polymer PVC, and again our favorite material PDMS, this transparent rubber. And the only important thing is that their Young's moduli, it's the counterpart of the spring constant of the material, are different by more than 3 orders of magnitude. This is giga, this is mega. They're very, very different in their elastic properties, in the Young's modulus. For this, should there be a super expert in the room, not in terms of the bulk modulus, only in terms of the Young's modulus. Aha. Okay, so the wave velocity, it turns out, scales like the square root of the Young's modulus. So this is a bit like epsilon here. This is the same as if in optics I could play with epsilon and change it by more than a factor of 1,000 without invoking a resonance. I know of nobody who could do this in optics, but in mechanics we can do this. You have contrast, and that's why you can make a structure that looks like that. That is again composed of soft, stiff, etc. rings. And the physics is very simple. If a wave is propagating in this direction, you kind of have stiff and soft regions in serial. And this is like having a stiff and a soft spring in serial. This is going to be effectively soft. And soft means slow in terms of mechanical wave propagation. If I look at the same position but a different direction of wave propagation, it's going to be a stiff and a soft spring in parallel. Now I have to compress the stiff spring, so it's going to be effectively stiff, which means effectively fast. So this is what I told you before. I want the wave to go fast in this direction and slow in this direction, and that's how I trick the wave and make it go around the object. Now it's a bit more sophisticated than in the thermal conduction case, because now I have to watch out that this period here is sufficiently small compared to the wavelength. And this is very aggressive. Actually, in this case, if you care, you have to make it 20, 30 times smaller than the wavelength. It's not very forgiving at all. You have to make it really small to avoid Bragg diffraction effects like that. And then we again have this trick that we perforate these layers to kind of continuously grade this distribution. In waves, you also always have the issue that apart from the phase velocity, you have to make sure that the impedance of the wave is the same everywhere. I didn't really mention that in optics, but that's another condition you have to fulfill. If you have impedance mismatched layers, this means you will get reflections at some inner interfaces, and that's nothing you want. You don't want backscattering of the wave, you just want to guide it gently around. So I'm hiding a few of the difficulties from you here. You must also match the impedance, which is actually not possible exactly, but you can do it at least approximately. Okay, here comes our experiment. It's very simple. We take this PVC plate and we drill and machine these holes into the structure. And then at the end we smear this PDMS, the soft plastic stuff, in all the voids. We let it polymerize, and then you can color, you can spray some paint onto this thing, and then it looks again like a homogeneous plate. And you can simply launch. This is a macroscopic plate. This object is like this big. Actually, this was an accident. The real experiment is very large. It's more than 1 meter in size, and the mechanical workshop drilled literally tens of thousands of holes into this thing. And Nicola Stenger, who did this experiment, then immediately filled all the holes with PDMS. He put the paint on top before he ever took a photograph of the structure. So we had nothing to document it. And then we couldn't convince the mechanical workshop to do the 100,000 holes again. So we only did it in a part of the structure. Actually, most of the work is to drill the holes in the surrounding here that you don't see anymore. It's just my excuse that I don't have a photograph of the entire thing. This is a euro coin here, just for size comparison. And then the experiment we do is very simple. We take a loudspeaker and excite waves from the left, and they move to the right. And then we look at the thing with a camera, and we stroboscopically illuminate it, and by that we take movies. And the light scattering changes a little bit depending on whether the plate bends up or down, so you can immediately take movies. So that's what you get. This is a movie, a measured movie of the object, of the scattering object. So what we do is we just fix, we clamp, we screw the center to something very rigid. So this is fixed, and you see scattering of an object like in any textbook, except that this is measured. You see there is backscatter, you see there is kind of a shadow if you want, and you see that these wavefronts are distorted because the wave, naively speaking, has to go around, and that's why you get these curved wavefronts here, every aspect of scattering. And if you now go to the cloaking structure, this is at 200 Hertz, it looks like that. It's not perfect, but it's pretty good, I would say, and others have said in particular the wavefronts are again straight on the downstream side, and we have eliminated this shadow thing that you have seen here. There is still some backscatter, and that's due to the fact that the impedance matching is not perfect, and this has to do with the mass density of these materials. And let me emphasize this again, this is a broadband effect. We've shown this experimentally. I don't show you all these movies. We showed it for a factor of 2 in frequency. Theoretically, it should be even larger. So in mechanics, these restrictions that I talked about in the beginning from relativity play no role because everything is at very small velocities anyway. So here you can cloak a macroscopic object in principle for a broad range of frequencies, which is not possible in optics. Who cares? Well, this was meant as a demonstration experiment, but our friends from Marseille are going in the direction of cloaking for seismic waves. And this is one of their papers. This is not from our group. And the idea is to just take this structure, and scale it up. Scale it up by a factor of 100 or 1,000, and then the structure wouldn't work for 6 centimeter waves. I think in the experiment I showed you, the wavelength was 6 centimeters or so. Scale it up, that it works for 10 or 20 meters wavelength for seismic waves that travel on the surface of the Earth. And as they argued in their paper, these are the worst waves in terms of earthquakes because there the wavelength roughly matches the size of buildings. And that's why these waves coupled so well to buildings and hence destroy buildings. There are all kinds of waves. There are also bulk waves that come from, I mean, if this is the Earth's surface, that come from underneath. But it turns out that much of the destruction of earthquakes comes from these Rayleigh waves that are traveling over the surface of the Earth. And just to embarrass myself, I didn't know much about these Rayleigh waves. They are amazingly undamped. You can even see Rayleigh waves that have traveled once around the entire globe and come back. People have seen these kind of echoes, that they have traveled once around the entire globe. It's amazing that you can see these things. And the idea of my friend Sebastian Gounod is to build such a structure, such a cloak, as I showed you, scaled up, and then the seismic wave would be guided around a building gently. Could be a nuclear power plant, for example, and then you would protect the nuclear power plant. And the important point is you would very gently guide the wave around the object, such that no part in the cloak would have to swallow a lot of momentum or have to swallow a lot of energy. Just in case some of you have the idea, let's just take a Bragg reflector for seismic waves in front of the nuclear power plant. Yes, you can do this. Then you will reflect the seismic wave. And if you reflect all that energy, you're going to have a huge collapse of your structure next thing, because this is a lot of momentum that hits you there. So it's a better idea you do it gently, adiabatically. And this is not a cloak. They are doing this in collaboration with a company called Menard. And they convinced them to drill all these holes. So to do the modulation, in this case, they have drilled holes that are 5 meters deep, and they have simply made a Bragg reflector. This is a Bragg reflector for seismic waves, just to test whether you get enough contrast and whether you get things under control, whether theory and experiment match up reasonably well. And they do. And now they have convinced this company to drill more holes and deeper holes. At the moment they're drilling 10 meter and deeper holes, and they fill them all up with concrete to get better impedance matching, and also it's more stable, I guess. And we'll see where this goes. This costs a lot of money. And first I thought this is insanity to drill all these holes. But if you compare the cost of drilling these holes to the cost of building a nuclear power plant, it's nothing. It's really nothing at all to drill these holes. So that's, I guess, why they care. And again, this company is putting a lot of money into it, and we will see where this brings us. But this was cheating in a way, because once again, in general, you have 3 polarizations in mechanics, and in this examples, we only had 1 polarization. What can you do in 3 dimensions as opposed to surfaces or membranes? Well, there are weird solids that have been predicted or suggested. For example, these so-called pentamode metamaterials. This is a 3-dimensional structure suggested by Graham Milton and Andrei Cherkayev. And the purpose of this structure is to give you a solid, effectively, that has a shear modulus that is very much smaller than the bulk modulus, like orders of magnitude smaller. And the idea is that the transverse waves are connected to the shear modulus, the longitudinal waves are connected to the bulk modulus. So if you make the shear modulus very much smaller, this means you make the transverse waves very much slower than the longitudinal modes, such that at some point you can simply forget about them. This is kind of a solid approaching a gas or approaching a liquid, in the sense that the shear modulus is very small, ideally 0. And you can see why this would work. Basically, this is a lattice of needles, and these needles touch at points that form a diamond lattice. I think you can see this. You have here one touching point in a quarter of the space diagonal. That's what you learn in solid state physics. This is the points here, these touching points, form a diamond lattice. And at this touching point, it's very easy. It takes you 0 force and 0 energy to change this connection. It's like an ideal joint. And hence the shear modulus is 0 for this structure. Whereas if you want to compress this structure under hydrostatic conditions, you would have to compress these needles themselves. And this is hard. So this was their idea. When we first saw this, we laughed actually, to be honest, because if you actually have these points touching here, it will fall. Next thing that happens is everything collapses, and it's a totally unstable structure. But then we asked ourselves, well, maybe it also works if we make this connection finite in size. If we go from a point to a small region, if the region is small enough, maybe we can approximate this case that the shear modulus is very much smaller than the bulk modulus. And if you care a little bit about fabrication, there needed to be a trick. I told you about this laser lithography. We came from optics, so we never cared about very tall structures. But then if you want to make structures for mechanics, you want to have higher, taller structures. And there is an issue. If you have a high numerical aperture lens and you focus, you do this carefully with oil immersion to get a numerical aperture of 1.4 or so. You have to have a well-defined glass substrate here, and then you get a focus here. And very obviously, if you want to move this focus up, you have to move the lens up, and very obviously at some point your lens simply bumps into the substrate if you expire the free working distance of your objective lens. And then you are at the limit of height you can achieve. And it turns out for high-end focusing conditions, this means you cannot make structures that are taller than 100 microns or so, which is too small to do mechanics experiments. There's also, if you care about optics, a very ugly effect, and that is that the refractive index of the glass and the photoresist are very similar. They are similar to the second digit, but the second digit after the comma is actually different by 1 unit. This doesn't sound a lot, but this means that under high focusing conditions, you get higher order aberrations that add up as you move your focus further away from the interface. And this means that even after going away 10 microns from the surface, you have a different intensity here than you had here, which means you have to do all kinds of ugly pre-corrections to get the same kind of structure here than you would have gotten here. And I'm telling you all this because there's a beautiful trick that Michael Thiel has come up with, and that we call dip-in direct laser writing, that uses the photoresist as the immersion liquid. So we go away from oil as the immersion liquid, put simply a drop of the photoresist onto the objective lens, and then we anchor the structure on the glass substrate and simply use the glass substrate to bring the structure up and down in the focus. And the beauty is the optical path length from the objective to the focus is always the same. So you can write, in principle, structures that are meter in height. In practice, you can go to a few millimeters now, and then the drop simply doesn't work anymore. You have to put some container or something. And here the aberrations are still there, but the aberrations are at least constant. They do not depend on the height. This is a point you cannot appreciate if you have not done things like that yourself. If you have worked for years to pre-correct crazy aberrations, and then all of a sudden you don't have to do this anymore. This is a miracle. This is actually not so old, this trick, and now pretty much everybody is using this. This has become commercial from the start. We actually have a little company selling this laser lithography instrumentation. And now everybody is pretty much using this. When I first heard about it, I thought, oh man, this is not a good idea. I would not have tried this. Why? Because if for some reason I expose the photoresist close to the microscope lens here, then it's exposed, it polymerizes. This means basically I've put a layer of glue on top of my microscope lens. This costs order 5,000 euros, and you will never get rid of this glue again. You have basically destroyed a 5,000 euro microscope lens by doing that. But the beauty is, what I told you hours before, that 2-photon absorption localizes the energy here. I told this story many times, but I didn't really believe that you would get nothing here, but you do get nothing. In years and years of using this, we have not a single time exposed the photoresist here, which would have been the death of the microscope lens. In any case, these are the experimental tricks. Here are some pentamode structures that Timo Bückmann has fabricated. This is a little cube structure here. Here you see a magnified version. You see these connections. These are the important part. In this case, they are around about half a micron in diameter. And this you have to compare with this 37 micron lattice constant. This means this connection is about 1% of the lattice constant. It's fairly small. It's a very thin connection. And for these parameters, trust me on that, you get a bulk modulus that is more than 1,000 times larger than the shear modulus of the structure. So once again, this is like a solid mimicking a liquid or mimicking a gas in the sense that it has very little shear to it. Let me forget about this. Forget about this here too. Let me see what I do not forget. Yeah, let me tell you this thing here, maybe as the last. So, can we use now this pentamode structure to build a mechanical cloak in 3 dimensions, rather than only on surfaces? So, in a way, I'm trying to make this P, this stiff P, unfeelable for the princess. She's kind of doing a tomography experiment on the P, and I do not want her to feel anything. This is not so serious. So it's a core shell structure with a stiff core. And what we do now is we add such a shell layer, quite similar to what I showed you before in diffusion. And here we play with a small connection such that in all the region, the bulk modulus is much larger than the shear modulus. But here in this red region, the bulk modulus is smaller than here. This is softer, loosely speaking. This is all one host material, all polymer. I'm just coloring this for illustration, otherwise you wouldn't see anything. It's a quite subtle difference here. And in this manner, you can kind of guide the force field around this stiff thing here. This is a magnified view. This is the game. We're making this connection here in this red region smaller than in the white region, and that's how we play with the compressibility, in other words, of the structure. And this is an optical image of the structure. At the time, we were quite proud that we can make such large structures by the dip-in technology, also by using galvo mirrors to scan the laser focus very fast. This has become so fast that you can do this in reasonable times. So for years and years, we have actually used piezo scanners to scan the sample with respect to the laser focus, and then you can get speeds of up to, say, 100 or 200 micrometer per second. If you rather scan the laser focus with a motorized, with a galvo mirror, then you can go up to speeds of the focus in the sample of a couple of centimeters, go even up to 10 centimeters per second speed. So this is like a 3 orders of magnitude speed improvement. This was humongous for us. Things that took hours and hours before are now ready in a few minutes, and you can do the next structure. So this is the structure. This is just to show that we can nicely play with this small connection. It's precise enough to do these kind of things. And then maybe I end with these movies here. This is, if you want, a tomography experiment, or in other words, we're pushing with a stamp. It's this thing that is going up and down at the top onto the structure. You see it from the side. It's an optical image that you're seeing. Just in case you wonder what you see, this is the glass substrate surface, and you just see a mirror image of the sample on the glass substrate surface. And let me describe to you what you see here on Earth. Let me stop this here and maybe look in both movies pretty much in the middle. So what you see here are the displacement vectors. This is how much a lattice point has moved. You can do this by cross-correlation analysis of these images. So here they pretty much move all down. And no surprise at all, if you look at the same plane here with this stiff thing underneath, you see almost no movement. This is like having a very, very stiff spring here in this region, and you don't compress this stiff spring, and you see a huge distortion of the displacement vector field. And so what we want is, we want this shell around the core to give us the same displacement vector field as you see on the left-hand side. And let's look at the movies here once again. First I let them circulate. This again the obstacle on the right hand side. The shell is fairly thin here, it's only in this region. And if you look at the cloak, you will see that in particular in the middle you have eliminated this behavior here. Hope you can see it. I'm going to stop the movie if I can. So let's again look at the point of maximum pressure here. You see again there's very little displacement for the stiff core, and here you pretty much recover the same thing as you had for the reference lattice. If you ask yourself, why on earth does anybody need this? One useful thing could be that you think of a stabilizing lattice, a construction in a bridge or something that stabilizes something, and then you think of punching a hole into this structure to have some feed through or something. Send another pipe through, a cable or something, and then this hole will very much destabilize your structure. And basically what the cloak does, it recovers the original stability of the stabilizing lattice and actually gives you, if you do it right, exactly the same properties as if you had not punched a hole for a feed through the structure in the first place. And I guess that's a good point to end. There are more fancy lattices, maybe you just look at them. So in the meantime, we have made improved versions, not just the core shell structure, but a graded lattice that does exactly that job that I showed you. This would be your stabilizing lattice here, and by this fancy structure, you can make this void, this feed-through, disappear in the sense that to the outside, the structure will look like a homogeneous lattice. These are the kind of games you can play. Yeah, and with this I just end and give you maybe time for a few questions. Thanks. Yeah.
Yeah, I have a question. You showed, basically you started at the beginning showing the mathematically analogy, and then you've shown that you and your group, you went very horizontal, let's say, very wide, and you showed that you can experimentally show that these things are equivalent, right? If you've seen it now back to back, and you actually see, for example, the mechanical thing, especially for me, so someone who doesn't do it, it looks almost identically the solution, the cloaking, as to the diluted case. So now I was wondering if you can comment on what is next, because if I remember correctly, you basically had a check mark at all the mathematical equivalents. So can you go wider, or do you have to move on in a different direction now?
Well, in mechanics, it's really not solved yet. This pentamode thing is again cheating in a way, because we go to a very special situation in which the shear modulus is orders of magnitude smaller than the bulk modulus. But normal solids, if I want to do this in a normal stabilizing structure, this will not be the case. There the shear modulus will very roughly be the same as the bulk modulus. So there these tricks still do not work. What I would have to do is, I would have to come up with a generalized elasticity tensor that goes beyond the ordinary, and generalized in the sense that for this class of elasticity tensors, this elastic equation becomes form invariant. And this has not been done, amazingly. Tomorrow I will show a little bit what we are doing in this direction. We can now make solids that have elasticity tensors that are totally outside of the normal. You have degrees of freedom that you do not have with ordinary elastic solids, but applying that to cloaking is still very far away. It's a quite complex problem, actually. But to the beginning of your question, I would not claim that I have shown that these different areas are analogous. I think this was pretty much known. I just remind myself that they're all the same, and this was for us an inspiration that we can use the same principle to do things in seemingly very different areas, but at the end of the day the physics is closely similar.
You at the beginning with light you talked about cloaking phase, or how in solar cells you don't care about phase. When do you care about phase? For instance, with the OLED wallpaper example, do you care about phase there? Or?
No, I mean in the diffusive regime there's really no meaning to phase in the same sense anymore. And as you have the OLED switched on all the time, it's pretty much stationary anyway. If you would care about pulsing of the OLED on a nanosecond scale and then looking with gated detection onto the OLED, it would make a difference, but who cares for this application? For other things you do care. I think in mechanics you would like to recover the same phase of the wave that you have sent in for some applications. So there you do care. I mean, the military also cares. I mean, they initially dreamed that they could cloak tanks or whatever, but you then have to do it also under conditions where it's robust to detection with pulses. And this I showed you is impossible. Maybe, fortunately, I don't know.
Sorry, just curiosity. I guess this story is a bit similar to going from the flat space in relativity, for example, to curved space-time.
Yeah, this is a delicate question. The mathematics looks actually very similar to general relativity. I only showed you the starting point with this Jacobi matrix and this transformation, but actually when you do it, let me go back. I showed you the equations in a Cartesian form. But then for this transformation of a point to a circle, you actually need it in polar coordinates or in spherical coordinates. So when you go from Cartesian to polar, you need the fundamental metric tensor of this transformation, and you need it once and to go back to Cartesian space again. If you put this all together, it's actually pretty scary. That's why I didn't show it to you, and the equations look very, very much the same as what you have in general relativity. And that's why some people who are good at solving equations in general relativity have been very good at doing these calculations in the early years too. So in this sense, it is similar. One mistake I have made in the beginning is that I thought it's actually the same, but it's not. Because we are talking about only transforming the spatial part of the coordinates, of the 4 vector. We're not transforming time. So actually, in the words of general relativity, everything that I talked about is flat space. It's transformed, but it's flat.
This was like so my question was about, can one create a black hole in this thing, but from your answer.
Look, I don't know. There are actually publications out there who talk about using these ideas of coordinate transformations for general relativity, and as far as I understand, people do not agree whether you can do in principle the same thing for gravitational waves. I mean, at the end of the day, this is not practical anyway, because you need humongous masses to do anything to a gravitational wave. This is more an academic question anyway. I think in principle you can do the same thing for gravitational waves. Yep.
I mean, the principles that you were discussing about the transformation and essentially the first part of your talk, can we use those to create the elements that are not reciprocal? And essentially you don't have, for example, you have like a unidirectional propagation of light, and the system is basically do not respond in the direction.
All the transformations I showed you are leading to reciprocal responses.
Are they?
Yes, absolutely. You can always just invert time and you will get the same result. And that is the case because I'm only playing on the spatial part anyway. I'm not transforming time. So everything I showed you is reciprocal, and you cannot use it to build Faraday isolators or something like that. There are some very few, very controversial papers out there doing transformations also with the temporal part, claiming that they can design non-reciprocal devices from that. But there is no agreement, no consensus on these papers. I think they are wrong, but I'm not sure. Very little has been done in this direction. Yeah.
In popular culture, cloaking is sometimes also used. Do you think we can get there?
I missed the beginning. Ken?
In popular culture, cloaking is also used.
In popular culture?
Like in Star Trek and in
Yes.
Harry Potter.
Yes.
Do you think we can get there?
Well, what I told you about the restrictions in terms of relativity is hard, I believe.
Yep.
So you can't do it broadband. So if the Klingons are invisible to Captain Kirk for all visible colors, I think this is not compatible with the laws of physics. But there are a lot of correct things in these movies. For example, if you remember, the Klingons had to lower their cloak before they could fire the laser. And that's a result of reciprocity that you asked about, because if light cannot get in, the phaser cannot get out either. So that made sense to me. But the broadband cloaking part, I think, is not consistent with physics. Sorry for that.
But they can also see the other ship while they cloak. Which is
Yeah, I mean, that's the dull thing about an ideal invisibility cloak. If people cannot see you, you also stand in the dark and cannot see anything. That's not very pleasant, I guess. Yeah, but anyway. I think we should make an end here, otherwise I get into trouble. So, see you tomorrow.